Before the launch, the Hermes spacecraft weighed in at approximately 110,000 kilograms and was stationary in low Earth orbit assumed at an altitude of 500,000 meters. Due to the force of gravity, any object in orbit, such as the Hermes spaceship, would be accelerating towards the center of a larger mass like Earth. However, the larger mass would also be rotating away from the object in question, which would cause the object to fall around the large mass rather than into it. This gives the object a constant velocity tangent to its orbit, which in the case of Hermes is 7,600 meters per second. The energy of Hermes at this point is 280 million kilojoules, with its kinetic energy being 6.66 billion kilojoules, and its gravitational potential energy being negative 6.38 billion kilojoules. The reason why gravitational potential energy is negative is due to the fact that it takes negative work to bring an object closer to a larger object. This develops the idea that gravity attracts objects and that kinetic energy grows as gravitational potential energy diminishes due to decreasing distances. To completely escape the gravitational well of a celestial body, one must first reach a speed known as the escape velocity. At 500,000 meters above Earth, it is 11,000 meters per second. Even though achieving this speed isn't a requirement, it is assumed that the Hermes achieved this velocity based on the launches in previous NASA missions. Over the period of 124 Sol, Hermes covers a distance of approximately 188 million kilometers in order to reach Mars. During this time, the spacecraft accelerates to 24,000 meters per second to match up with the orbital velocity of Mars at the time, which is assumed to be equal to the average velocity of Mars. This would make the velocity of the ship 0 meters per second relative to Mars, allowing the crew to descend to the surface vertically rather than on an angle and not having to worry about horizontal velocity.
It is also assumed that Hermes ends up at an altitude of 400,000 meters for the duration of the 6-day mission low Mars orbit. If the Mars descent vehicle weighs about the same as the Apollo lunar probe, which is roughly 16,000 kilograms, it would reach a maximum velocity of 257 meters per second. This is also known as a terminal velocity, which is reached when the drag force caused by collisions between the object and atmospheric particles equals the force of gravity of 59,200 newtons, resulting in force equilibrium. At this point, the thrusters can easily apply an upwards force to bring the craft to a safe landing velocity. The terminal velocity was determined using the drag coefficient of a flat plate, which is to represent the circular face of the cylinder body of the MDV, the air density of Mars, which is 0.02 kilograms per cubic meter, and the reference area, which is the surface area of the reference lunar module. The force of gravity was found using Newton's second law, which states that a force applied to an object is proportional to both its acceleration and mass. This relies on Mars's force of gravity, which is 3.7 meters per second per second. However, in order to achieve such a speed, 30,200,000 megajoules of energy must be added to the system via onboard thrusters, providing the craft with an average acceleration of 1.21 millimeters per second per second. Assuming that the Hermes maintains this velocity, the crew, minus Mark Watney, makes its way back to Earth in 236 days, traveling a distance of 502 million kilometers.
After that time elapses, the crew aboard the Hermes arrives at Earth, but have decided to divert course back to Mars instead of returning to Earth's orbit. In order to do so, they perform a maneuver known as gravity assist. By flying within close proximity of Earth, the spacecraft is able to adjust their trajectory by what seems to be 45 degrees. At the same time, the spacecraft manages to gain about 10,000 meters per second in velocity, giving it a final velocity of 34,000 meters per second. This is determined using the following rationale. The initial and final velocity v are equal to each other relative to the planet. To translate the relationship to the Sun reference frame, and to find the true velocity relative to the solar system, these aforementioned velocities are treated as horizontal and vertical components of the final velocity relative to the Sun, with the change in trajectory being the angle. In this case, a special triangle is produced, with the hypotenuse being root 2 times either side. Therefore, the final velocity would be 1.6 times the initial. This may seem impossible, as the laws of conservation energy state that energy cannot be created or destroyed, and yet it seems that the craft gained kinetic energy out of nowhere. However, the energy gained actually comes from the Earth's kinetic energy, thus accounting for the boost and adhering to energy laws. This maneuver barely affects the velocity of Earth, but greatly impacts the vessel. At this new speed, the Hermes travels 945 million kilometers in 322 days before reaching Mars again. Assuming that the Mars ascent vehicle is identical in mass to the descent vehicle, 16,000 kilograms, the craft must achieve an acceleration of 112 meters per second or 11.4 Gs, and reach an altitude of 9,180 kilometers to match with the speed of the Hermes. This is also assuming that the launch time of the MAV matches the usual launch time of a NASA shuttle, which is 9 minutes. If the vehicle is launched correctly, the speed and direction of the Hermes and MAV will match up, resulting in a velocity of 0 meters per second relative to each other. In order for any of this to work, the orbital speed of Mars at that moment must also be identical to that of Hermes. This increase in velocity can be explained by Kepler's planetary laws. The first law states that planets orbit around the Sun in an ellipse, with the Sun being at one of the foci. Due to this, the distance between the centers of two celestial bodies is always changing throughout the orbit. This change in distance inversely affects their centripetal acceleration of the orbiting mass, which would then in turn affect its orbiting speed. This ties into the second law, which states that planets constantly change velocity over the orbiting period, thus accounting for the change in velocity of Mars. After this rescue occurs, the crew along with Watney travel for an additional 620 million kilometers in 211 days, before returning to Earth again. And this is how they brought the Martian home, yet again.